Hello friends, welcome to lecture number 2, and here we are going to discuss about De Morgan's theorem. Before that, we must know some properties of Boolean algebra. So first I'm going to give you the properties, then we're going to prove this De Morgan's theorem. Okay, this is very important topic of Boolean algebra. Okay, so before we start, please subscribe the channel if you are new to my channel. Okay, and if you want to follow me, then you can follow me on Insta. lec2 is my ID of this Insta ID. This is Insta ID. So you can follow me on Insta, and you can suggest me any course that I should create on my channel, any topic of physics. Okay, so let's start now. Now you see, if A, B and C, these three are logic variables, three logic variables are there, then they're going to follow this commutative property, which is A plus B is equal to B plus A here. So here plus represents OR gate. Similarly, next so in case of AND gate also, it's gonna obey this commutative rule: A dot B, B dot A, right? Now associative. Number 2, associative property. A plus, within bracket you have B plus C, then it can be written as A plus B, then plus C, right? Similarly, in case of product as well, they can be written this way: A dot, within bracket B dot C, then within bracket A dot B, then dot C, right? Then you're gonna have distributive property. Distributive property, that's you see A plus B dot C, then it can be written as A plus B dot A plus C. This is very important property. Okay, remember this. Also, you're gonna have this property as well: A dot B plus C, which is gonna be equal to A dot B plus A dot C, right? Then involution. Now you see, now complement of A, and again if you take its complement, or you can say not get, right? A bar represents not A, right? If you take not of not A, that is A bar, again not of not A, then it's gonna be again what? A, right? Suppose if you put A is equal to 1, then if you take A not, that's gonna be 0. Again, if you take not of not get A, then it can be again 1, right? That's a very simple thing. Now we're gonna have more properties added potentially. So here you can see, first we're gonna have here A plus A, that's gonna be A. That means here A plus means OR gate. So here A plus A, that's going to be A, means here you see either if you put A is equal to 0 or 1, doesn't matter, result going to be A. That means if you put 0 here, A is 0, that means this A will be also 0. So if these two are 0, then it's going to be 0, that is also A, right? Then if you put 1, A is equal to 1, then this A is 1 means that A is also 1, then result will be also 1. So that is the logic. Okay, so hope you have understood this. So similarly, you're gonna have A dot A, that's gonna be A, AND gate. So now next you're gonna have 1 plus A, that's equal to always 1, because you see So one logic variable is already given 1, and plus means OR gate. A is equal to, now doesn't matter what going to be the value of A, but if one variable is 1, then if you apply OR gate, then the result always must be 1, right? Then similarly 1 dot A, that's gonna be A, right? So when you put A dot 1 dot A, it represents AND gate. In case of AND gate, to get 1, both the variables must be 1, and to get 0, any one of them must be 0. But here you see, one variable is already 1 here, so it depends, its results depends on the A only. So whatever be the value of A, that's going to be the result here. In this case, if you put 0 here, then it's going to be 0. That means if you put 1, then it's going to be 1. So that's why 1.1 A1 dot A, we can write A. So hope you have understood this. So now let's move on to next property, that is 0 plus A, that's going to be A, and 0 dot A 0 dot A is 0, okay, right? 0 dot A is 0. These are simple properties, right? So now let me go to the next slide. Okay, now you see one more very important property. If you have A plus A dot B, or simply you can say AB, then you can write A. Okay, because you see, when you take A common from here, then you're gonna have 1 plus B. Then I have already just given you that here. You see 1 plus A is 1. Similarly 1 plus B, that's also going to be 1, right? Because we have OR gate here, OR operation. So in this case, if you have OR operation, then it doesn't matter whatever will be the value of B. If one variable is 1, then result always going to be 1. So that's why it is going to be 1 into A, that's going to be result equal to 1. So hope you have understood this property, right? So now next property is, if you have A into A plus B, that's going to be equal to again A, right? How it going to be A? Let me tell you. A dot A plus A dot B, here you're going to have, and A into A, we have already got that here. A dot A is A, so that's why this is going to be equal to A plus B, right? And if you take according to this property, this is going to be equal to A, right? So that's why we have got A into A plus B, that is A. So hope you have understood this. So if you multiply this one, these two, then you're gonna get this step, and A dot A is simply A, and if you take A common, then you're gonna have A plus 1 plus B. You can say like this also, or directly you can use this property, this is equal to A, right? Or you can use this property 1 plus any variable, that's going to be always 1 into A, that's going to be A, right? So that's the thing, very simple thing. Okay, so hope you have understood this. Now let us discuss about the next property. Okay, that is also very important property. Here you must know this one, A plus, so not A into B, that's going to be equal to A plus B. Okay, A plus not A and B into B, that's going to be A plus B. Okay, now you see already we have got this property. You can say this one, according to this property. Let me copy this one. Okay, let me paste here. So according to this property, if you compare B with C and A bar, that means not A, with B, then A plus not A into B, then replace keep A as A, B is replaced by A not, and A plus C is replaced by B. Okay, so C is replaced by B and B is replaced by not A. So then you're gonna get this, and a plus not a, that's gonna be 1, a plus b, and that is a plus b. That's how we have got this property, right? So then you're gonna have one more property, very important property, that is a into not a plus b, not a plus b, that's gonna be a b. Okay, then you're gonna have a plus a naught. A plus a naught is 1, right? A plus a naught is 1. Just simply it is a OR operation. So if a plus a bar, you have not a plus not a. If a is 1, not a gonna be 0. 1 plus 0, that's gonna be 1, right? This is OR gate. If you put a is equal to 0, then not a gonna be 1, then also it is 0 according to an OR operation, right? So now look at these things, and a dot not a, that's going to be always 0, right? So these are the, now let us prove De Morgan's theorem. Okay, now let us prove De Morgan's theorem. So first let us prove this one, first one. So number 1, okay, let us consider that x is equal to a plus b, suppose, and y is equal to a not a dot not b. Okay, now here we need to prove that this is equal to complement of this. Okay, that means a plus b not, right? We need to prove this one, this is equal to this one. Okay, so now you see, first let me tell you, suppose you have two variables x and y. If they satisfy this condition, this is equal to 1 and this is equal to 0, then x complement of x is equal to y, or you can say x is equal to complement of y. Okay, they must be complement of each other, then only these two conditions will be satisfied. Because here you see, this can be 1 if both equal to 1, or any one of them must be equal to 1. So here in this case, if both equal to 1, you cannot get 0 here when you apply an operation. If both equal to 0, then you gonna have 0 here, but if both equal to 0, you're not gonna have 1 here. So to satisfy both the condition at the same time, then one of them must be 1 and another must be 0. Then in that case, 1 plus 0, that's gonna give you 1, and 1 dot 0, that's gonna give you 0, right? That means they must be complement of each other. So hope you have understood this. So if we are able to show that x complement is equal to y, then we can show that x complement means x is, we have considered a plus b, and y is this. Then we will be able to show this, right? So now let me prove this one, how to do that. So it's very simple. So now let me clean these things first. Okay, so let me clean it. First you see, let us find x plus y. X plus y, so that's going to be a plus b plus not a dot b, or you can say complement a dot b here. So here we're going to apply this identity that we have already discussed. So that's why I have given the properties earlier. That we have already got this property, that is a plus a complement b is equal to a plus b, right? We have got this one. So now compare that this a and this b, and this a bar is b bar, then this b is this one here, you see. So you can write this way, b plus b bar a bar. These things I have written this way. So if according to this formula, you should get b plus a bar, right? B plus a bar. So hope you have understood this. So using this identity we have to get this one, a plus b plus result of this is nothing but b plus a bar. So let me write this identity here where I have used this one. Okay, now you see a plus a bar, right? So a plus a bar is nothing but 1, so we can write here a plus a bar, that means a complement plus b. So this is gonna be 1, so we can write here 1 plus b, and 1 plus b, that's gonna be b, right? Because we have already just let me write the region here, 1 plus a bar, sorry, a plus a bar, that is equal to 1, right? Let me write this one here. Since this, so then again 1 plus b is nothing but 1 plus b. So as we have already got one variable is 1, and here we have OR operation. In case of OR operation, if one variable is 1, then it doesn't matter what is the value of the other variable. So that's why it always gonna be 1, because since we have already got 1 plus a is 1, we have already got this one. So hope you have understood this. So now we have already got x plus y is equal to 1. Now let us show that x into y is also 1. 0 is 0. So now you see now so we are solving this one only, okay, don't be confused. So here this is the continuation of this. Let me go to this part. So here let us find x dot y. That's gonna be a plus b into complement of a dot complement of b. Now here you can see what you can do here. If you apply the distributive property, you're gonna have a dot a complement dot b complement, plus then you're gonna have b dot a complement dot b complement. Okay, so here you see now a dot a complement is 0. Similarly, b dot b complement will be also 0. So that's why this whole thing is 0, since a dot a complement is 0, right? Is 0. So in case of AND operation, if one variable becomes 0, then the whole result must be 0, right? So now we have got, since we have got x plus y is equal to 1, x dot y is equal to 0, and this condition will be, it is possible if only here you see, if both equal to, as I have already explained, if both equal to 1, then you're gonna have 1 here, but you are not gonna get here 0, right? That's gonna be wrong. So, and if you put both equal to 0 here, then you're gonna have 0 here, not 1. But here you're gonna have 0, though you're gonna have 0, but this condition will not be satisfied. So that's why, to satisfy both the conditions, so one of them must be 0 and another must be 1. That means one must be complement of the other. So that's why, so therefore we can say y is or we can say therefore x complement is equal to y. And if that is the case, then we can write x complement means here x is a plus b, so complement of a plus b, and y is a complement dot b complement, right? And this is the first identity. This is the first theorem, De Morgan's theorem. So now let us prove this one. Let me copy this one and let me go to the next slide. Okay. So here is the theorem. Okay. So in order to prove this, let us take the right hand side. Okay. Let us take the right hand side. There is complement of a plus complement of b. So we have already got that not of not a, or you can say complement of a, complement of complement a, that is a, right? We have already got this. So here it can be written as complement of a complement plus b complement. We can write that way, right? Since complement of complement a is 1, sorry, not 1, a. So we have applied that, right? And we have already got that in the first De Moivre's theorem, that we have already got that complement of A plus B, that is A complement dot B complement here. Now consider this complement A as A now and complement B as B now here. So then applying this, what we're going to have here, we're going to have complement of complement A plus complement of complement B. That's what we're going to have since this, right? This is the first De Moivre's theorem, right? And again we have got that complement of complement A is A, so that's why this thing's gonna be A, right? And this one gonna be B, right? And this is your nothing but just wait. So what we have got, this one A and this one B according to this property. So hope you have, this is nothing but your left hand side. So hope you have understood this. That's how we can prove the De Moivre's theorem, the second one. Okay, so hope you have understood this. So hope you like the video, and hit the thumbs up button, share with your friends, subscribe the channel if you are new to my channel, and stay connected. So